This is Unit 2, Lesson 6, Proving Lines Parallel. It corresponds to Lesson 3.3 in the textbook. So the first question posed, are lines L and M parallel to each other? How can we tell? Well, one way to tell if lines are parallel is if we have the arrows in the diagram. Or if the information is given to us, which is essentially the same. Looking at this particular diagram though, lines L and lines M don't have any markings. They sure look parallel, but we can't necessarily be certain. So how are we going to go about this? How could we prove that lines are parallel? What if we take what we've been learning and apply it backwards? We know, for instance, that if lines are parallel, then certain relationships are true. What if we reverse it? And what if we were given that the relationship was true? It would then make lines parallel. That's the idea of what we're going with today. We're going to take all of these concepts of if lines parallel and reverse them so that we can prove that lines are parallel without necessarily being given that lines are parallel. So here's a warm-up question for if you would be in class. It says, write the converse of each statement. We worked with converse in the first unit, and the idea of a converse is that it reverses the if and the then in a conditional statement. So the first one says, if two angles have the same measure, then two angles are congruent. The converse of this is when you switch them around. So I have it pre-typed in here. So the converse of this statement reads the other way around. If two angles are congruent, then the angles have the same measure. Same thing. If angle 3 and angle 4 are complementary, then the measure of angle 3 plus the measure of angle 4 equals 90 degrees. If you take your hypothesis and conclusion and switch them, you have what's referred to as the converse, which would read, if the measure of angle 3 and the measure of angle 4 equal 90, then angle 3 and angle 4 are congruent. What we're going to do is we're going to take the idea of these two, or not these two, but the idea of a converse and apply them to parallel lines as well. So for instance, take a moment and fill out this chart. Notice it says corresponding angles converse. If two lines and a transversal form corresponding angles that are congruent, then the two lines are parallel. Alternate interior angles converse. If two lines and a transversal form alternate interior angles that are congruent, then two lines are parallel. So on and so forth. If two lines and a transversal form same side interior angles that are supplementary, then the two lines are parallel. This is a lot of words. I'm okay if we abbreviate. For instance here, if same side interior angles are supplementary, then lines are parallel. Then lines are parallel. I know that as we were writing if-then statements, some of you were starting to abbreviate shorter and shorter and shorter and shorter. This is pretty much as short as I'm going to accept. So if a relationship is true, if corresponding angles congruent, then lines are parallel. Tells me what needs to happen in order for lines to be parallel. So let's look at a couple of examples. Number 3 says, is there enough information to conclude that lines P and Q are parallel? If so, explain. So looking at the first one, I see degree with x's. Notice they're both the same variable, telling you that that measurement is the same, whether it's 60 or 20 or whatever measurement, it's telling you that an unknown measurement is the same. What kind of angles are you looking at? These two angles are alternate interior. Alternate interior angles need to be congruent. So the wording for this one would be, yeah, you can conclude, well, it says P and Q, I guess these are lines A and B, but you can conclude that these two lines are parallel because if alternate interior angles are congruent, then you know that lines would absolutely have to be parallel. Look at letter B. Letter B, for instance, we have 85 degrees and 100 degrees. These angles off the bat have no special relationship. They're not corresponding or alternate interior or same side interior or any of that. That doesn't necessarily mean that that the lines won't be parallel. It just means we might need a little more reasoning. Let's look at it again. So they may not be corresponding or alternate interior or any of that, but using vertical angles, I can move the 100-degree inside here. By moving it inside using vertical angles, I've created same side interior angles. Same side interior angles need to be supplementary. Let's check. 100 plus 85 does not add up to 180 degrees like it needs to. So no, there is not enough information to conclude. Same side interior angles should be supplementary in order for lines to be parallel. I drew these lines as if they were parallel, but if you were to actually go to the applet that we used at one point with all the lines and the angles, or if you were to draw this out, these are not actually parallel. Letter C. I'm wondering whether these two lines A and B are parallel. Let's look at what we have. There's no angle measures and there's no variables, but there are markings. These markings deal with vertical angles. Vertical angles are congruent. However, are vertical angles enough to show us that lines are parallel? The answer is no. Vertical angles are only created by two intersecting lines. If you go back and read all of these words, it says if two lines and a transversal form. If two lines and a transversal form. Even though that is very wordy, it's what's needed to understand the idea of why vertical angles aren't enough. Vertical angles are not created by two lines and a transversal. Vertical angles are created by intersecting two lines. So no, they have nothing to do with parallel, so that's not going to help us. A true statement, vertical angles are congruent, but not enough to conclude that lines are parallel. So now let's look at these other markings. I have a single marking and a double marking that I marked in red. The single marking and the double marking are there to show that you have two different angle measurements. If you look at these two, they're alternate. Oops, I made a mistake way back here. Should have said exterior. These are alternate interiors, and alternate interior angles need to be congruent. However, one has a single marking, one has a double marking. So no, these angles are not congruent. So these lines cannot be considered parallel. Again, I drew them to look as if they were parallel, but they're not necessarily if they were drawn to scale. Backside. It says find the value of x that would make, and again, I have P and Q. I think that should be A and B. That would make A and B parallel. Reasoning. These are alternate interior angles. So if alternate interior angles are congruent, then the lines are parallel. Again, students are going to ask with reasoning. Does it matter which way the order goes? Yes, it does. We used to write if lines parallel. These lines aren't parallel yet. We're trying to say that if these angles are congruent, if I set them equal and find the value of x, it's essentially saying that when x is 35, then these angles are congruent, then the lines are parallel. Same thing with letter B. These are corresponding angles. If corresponding angles are congruent, then lines are parallel. So if they're congruent, meaning if they're set equal, and I get x by itself, when x is 60 degrees, then the corresponding angles are congruent, which means then I have enough to prove that those two lines are parallel. So the order that you say things will matter. And then lastly, these diagrams or these theorems down here in this diagram aren't used a ton, but they're worth mentioning. So the first one is called the two parallel lines theorem. It says if two lines are parallel to the same line, so if two lines are parallel to the same line, then they're parallel to each other. So what I have drawn, and let me try that one more time. If two lines are parallel to the same line, then they must be parallel to each other. So if I were to call this A, B, and C, the single marking tells me that lines A is parallel to line B, and the double marking tells me that line B is parallel to line C. So this property is allowing me to say that since they're both parallel to B, A must be parallel to C. Not used a ton, but worth mentioning. Two perpendicular lines theorem says in a plane, if two lines are perpendicular to the same line. So if two lines are perpendicular to the same line, so here's line A, it's perpendicular to line C. Here's line B, it's also perpendicular to line C. Then it must both show that A is parallel to B. So let me write that out for you. If A is perpendicular to C and B is perpendicular to C, then this property is allowing me to say that A is parallel to B. Look at that for a second. Why would it be parallel? These theorems that we worked with today, these converses, these are corresponding angles. If corresponding angles are congruent, then lines are parallel. They are congruent because they're perpendicular, which means they're 90. Perpendicular transversal theorem says in a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So think this through for a second. Let me draw this diagram. I have line A again, line B again, and I'm going to call this T for transversal. In a plane, if a line is perpendicular to one of two parallel lines, if you know these lines are parallel, and the transversal is perpendicular to one of them, we know that if lines parallel, then, for instance, corresponding angles are congruent. So we know that T is perpendicular to B because of this idea of ordering that if lines are parallel, then corresponding angles are congruent. It worked vice versa over here. When we showed if corresponding angles were congruent, then we knew that lines were parallel. So the purpose of these three theorems is just to extend the idea of when the order of the if and the then need to be used. That's going to conclude this video. There are more proofs in the notes, and they will be done either in class or in another video. Thank you.